And we'll see how many people are out there watching us or listening to us as we hopefully go live. Yeah, okay, we are live on the Into the Impossible podcast network, joined by a very special guest. It's not so often you get a guest who's who's a friend, who's a fellow experimentalist, who's an inspirational person to me personally, and someone who rejected me and didn't take our offer to come to be a professor at UCSD. That hurts. We will have to get over it, but it's Professor Ina Vishik, who's a professor at UC Davis. Ina, how are you doing today?
I'm good. Wow, calling me out. So I'm a longtime viewer of your pod, so happy to be here.
Yeah, it's great, and hope to get in person again. I think. Well, one of the last times I saw you, I know, was at your wedding, but the other time was at MIT when you took me around and gave me a tour there. It's so gracious of you, and I hope to visit you up at UC Davis if they'll have one of us Southern California types up there. But you're an expert experimentalist, and you do research into the physics of superconductivity along with a large team of researchers. You've written many papers, and this is sort of partially I should say this, it's way more in your ballpark. I'm getting emails and texts from my brother, from David Friedberg, who's a big time billionaire investor, the one of the besties on the All In podcast. He's asking me, what do you think, and I'm getting hints of people like, should I start shorting Nvidia stock? Is this the end of semiconductors? The stakes are really high, as you know. This could really transform the world. I made just a small list as a hook to the listeners and the viewers out here, and I want you to add your own as well. But we're going to put up a link to some of your tweets that have been really helpful to me in knowing how to assess these counterclaims and claims. And we may be lucky enough to be joined by past guest Jorge Hirsch down here, who is not so sanguine that this is a real effect, and I think we'll be back with him later on. I'll put a link to our previous chat earlier this year. These reports of room temperature superconductivity are coming faster and more furious than the Padres' hopes are being dashed at getting into the playoffs. But here's just some of the things that I've been thinking about that high temperature, room temperature, ambient pressure superconductors could give to us. And I want you to add your own and pick your favorite. Energy transmission, zero resistance transmission could revolutionize power transmission, making it more efficient, reducing global warming effects. That's a certain benefit of a ambient temperature and pressure superconductor. Transportation, levitating trains, we've all seen that, and that will be key in what we get into with the Meisner effect, which you've forgotten more about most of the stuff, Ina, than I'll ever know. Healthcare, we had recently had an MRI, and we used one of those. Oh, Professor Hirsch is joining us. Let me add him in. Jorge is in the green room. Jorge, can you hear me? I don't hear you, Jorge. You're muted. There we go.
How do
Yes.
I? Oh,
Now we hear you. Can you hear me? Okay. I don't hear you now, but I heard you a second ago. You're muted again.
can you hear me now?
Now I do. Now I do. Welcome, Professor Jorge Hirsch, past guest on the Into the Impossible podcast. And we're joined with Ina Vishik. Do you know each other?
We have met. Yes. Hi, Ina.
Hi. I don't see you yet, but I hear you.
You may not be able to see each other, but the audience can see you, and that's the most important thing of all. And we will be taking questions from the audience because
Shall I try to use another browser and see if we can do this?
no, it's fine, Jorge. It's the audience sees you, and Ina can. I'll do a sketch of what Jorge looks like. um, Jorge, thank you for joining us. We're talking about all the potential technological breakthroughs that could be enabled, from healthcare to energy transportation to the power grid, reducing global warming, quantum computers. I'm also getting asked questions about, is this going to impact the stocks of semiconductor manufacturers? Chamath Palihapitiya, who's a bestie, along with my friend David Friedberg, past guest, who's very interested in your thoughts on this, and mine are less knowledgeable than yours. Let me first start with Ina. As an experimentalist, How did these results strike you? We've all been let down before, and we've all been accustomed to this kind of dream kind of dissipating. But how did it first strike you? What were the first things you wanted to know about this sample? I guess, what should we call it? LK99? Is that what you cool kids are
Sure.
calling? Okay.
Sure. Or copper doped lead apatite if you're more technical, but LK99 works.
Okay.
Yeah, so I'm happy to hear that you're also a fan of the All In pod. I listen to it on my commutes. I love it. Yeah, so my first response or my first reaction was no. The reason being that if you're in this field, there are these so-called unidentified superconducting objects, like new claimed high temperature, room temperature superconductors that pop up reliably every year or so. So, you kind of build up a thick skin to be critical about them. But I guess reading more into it, the upshot is, and we can go into more details why I think this is the case, it's probably not a room temperature superconductor.
Wow.
However, my feeling about it has sort of evolved into cautious curiosity. So that's not the same as cautious optimism, but uh, I do think that there might be something interesting there. And I am cautious because curiosity still requires mental resources and time. I guess as far as the potential impact on the world, that's another place to be cautious. So what I can say definitively is that materials science and materials physics and materials chemistry has had a tremendous impact on the world throughout human history, and especially in the 20th and 21st century, and it will continue to do so. Whether that impact will come from room temperature superconductivity or other innovations in that research area, I think the other innovations are more likely. So I think at this point, we probably do not have a room temperature superconductor. We might have one in the future. There's nothing that strictly prohibits it. But what nature has shown us so far is that superconductivity shows up in many different materials. When/if a room temperature superconductor does show up, we don't know what properties it will have. So among superconductors, we know some of them can sustain a large current, some cannot. Some really expel all their magnetic field, others have a lot of trapped flux. Some are ductile and can be used to make wires, others not so much. Some have good native oxides, which is important for making devices for quantum computing, and some do not. Some are made of earth abundant materials and can really, be deployed worldwide, and others are not, and so on and so forth. So, without knowing a material, it's hard to know potential impact.
So Jorge, are you able to hear us now?
I can hear you. Can you hear
Okay.
me?
Yes, now I do. And yeah, you don't need to call back in. If you don't see yourself, it's just because I'm focusing on Ina or myself, as I often like to do. So Jorge, you and I talked back a couple months back on the announcement of the previous, claim of a room temperature superconductor. Now I want to ask you, when you heard these claims, they're quite different than the types that we talked about back in February, March, around the time of the APS March meeting, when all hell broke loose in this group by Rango Diaz and all. This is a totally new group. Apparently been working on this for at least 24 years, maybe more. And it has a lot of people convinced that it's not only room temperature, ambient pressure, but it's been replicated. In fact, it's being replicated online on Twitch and other other venues that I'll display. Jorge, how did this result shock you, and what do you make of it? What's your immediate take to it?
Well, that's a interesting question. The answer is as I told you by email, when I first saw the preprints in archive, and even the video that they first posted, I said, this is not right. This is not superconductivity. The graphs look really crappy. The resistance drops like a rock. It's not what superconductors do. The theory arguments they give make absolutely no sense to me. So this is not right. And in fact, the first video was totally consistent with this just being magnetic, ferromagnetic, which you would be able to kind of put it at an angle like that by just repulsion of the same poles of a magnet. And so I was totally convinced this was uninteresting and surprised people were paying so much attention. Now I actually changed my mind. I actually, when I saw the second video that the Chinese group posted, then it is very clear from that video that this is not ferromagnetism. So this is clearly either diamagnetism or superconductivity. I don't think there is any question. That's a very tiny particle that does show this property, that it repels magnetic fields no matter what is the polarity. Okay, superconductors do that, and diamagnets like graphite also do that, but it's much weaker. Okay, so I then changed my mind, as I said, and I'm very open to the possibility that this is real, even though now what does it mean it's real? It means that they have have regions of it that may in fact be superconducting. Now there is an inherent competition between lattice stability and superconductivity. So it's very possible that this particular structure is very unstable, so it can only be stabilized within small regions of a larger sample. And so it's a very open question in my mind whether this will ever be like a bulk superconductor that can be useful for anything. But I certainly do not discount, and I think there's a very strong possibility that there is traces of superconducting materials in these samples that are doing these remarkable things.
And if it would,
let me just add one thing I would like to say. For the hydrides, I was always very convinced that they are not superconducting, and certainly Rangadia's work, I think, is clearly not right. That's because they relied on light elements, which I do not believe have anything to do with superconductivity. This is different. This doesn't have light elements. I guess oxygen is not very heavy, but most of it is lead and copper. And so in my view of superconductivity, this material could well be a superconductor because it's somehow similar to the copper oxide materials. In particular, it has anions like oxygen minus minus, or even phosphorus minus 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 could be in there, and those could potentially be giving you the physics that I think is responsible for superconductivity. So I'm very open to believe this may be right.
Wow, that's a huge change and very, very high integrity to admit that you could be, kind of led to be persuaded that this might be real. I've known you as a cautious, as an optimistic pessimist, but this is, I should say, the most optimistic I've heard you about such materials. Let me ask Ina, what if this is partial, kind of, it's superconducting. I happen to have a sample. I smuggled it out of Korea last night. No, I didn't. This is just a meteorite, which you can get when you go to my website, briankeating.com, but especially .edu addresses, students, and so forth. But let's say this is a superconductor, and but only part of it is, maybe it's like almost like a one-dimensional, vortex or would that change the magnitude of this discovery? Let's say we could only get it in a very compromised state. It wouldn't be, superconducting for miles like niobium titanium. We use it in every application in our lab. What would that mean if it's just kind of almost like a topological singularity within a bulk material? Would that quash your hopes or dreams, or how would that affect you?
I was so excited that you had such a large chunk. You got me there.
Sorry.
So the scenario you describe is actually something that happens quite a bit in the discovery of new superconductors, or has historically. So I haven't been a synthesis person since my undergrad days. But the general story is, when people are looking for new superconductors, the first result is often something, a phase impure specimen. So you have like a little pocket that is superconducting, and the rest is not superconducting. And then you maybe you see a blip in the resistivity, it doesn't go all the way to zero, or a blip in the magnetic susceptibility, suggesting a little bit of expulsion magnetic field. And then the people that are experts in this, they find ways to single out which minority component is actually superconducting, and make more of it. So if that is what's going on, that's kind of a tried and true path to getting a larger scale superconductor.
So we have the brightest audience in the known universe. Here's a question immediately from someone by the name of Slam RN, which I was going to call my second child, as you guys know. The South Korean team claimed that a compound of lead, copper, phosphorus, and oxygen is a superconductor at temperature above 400 Kelvin and ambient pressure. Did that raise your attention at all, Jorge? I mean, now it's not just a superconductor at ambient. Now it's superconducting when it's on fire. How do you react to this question by Slam RN?
Yeah, I do not have a problem with the critical temperature being 280 Kelvin or 300 Kelvin or 400 Kelvin. I mean, we are talking about factors of less than 2, and I mean, the cuprates are superconducting at 150 Kelvin. And once we know that's possible, then I am not, I mean, I believe that superconductivity originates from a delicate balance that involves very strong forces, Coulomb interactions. And so some small change in that balance can easily change temperatures by a lot. Now, it is true that there is a lot of competition with other things and with lattice stability, as I said, and so on. But no, the fact that it's 400 Kelvin rather than 300 Kelvin does not really make...
And Ina, my friend, Memes of Destruction, which is also my daughter's name, he asked, would it make sense to search for other compounds by replacing similar atoms in the periodic table column, namely copper atoms with silver, etc.? Thank you, guys, he's adding. What if you replaced it with other elements in the same column of the periodic table? Would that bear fruit in a certain sense?
I mean, if that's how you want to spend your time, then... I mean, in historical searches and optimizations of superconductors, there were some elements of serendipity. There were some elements of like deep chemist intuition built up over decades. I would say the first order of business would be to try to replicate the present results, and also just be very clear about what they show and what they do not show. Like, for example, a characteristic of a superconductor is zero resistance. In their graph of resistance, it's not really zero. The y-axis is it's actually not a small resistivity.
So I'm going to play, hopefully I can play this video here. Maybe not. It's not seeming to be working. Let me get out of this then. I had some animations that I wanted to show from my friend Richard Bahil at Santa Barbara, who works on these materials. I'll put links in it when I finally do get all this set up to broadcast the screen share. So how do these compare, Jorge, with the cuprates or with the the previous record holders? I mean, isn't it a substantial, almost of different quality to have superconductivity, raised almost doubled in temperature? I mean, aren't these things fundamentally different, or is it possible that these are just sort of a perturbation in some materials phase space away from one another?
Yeah, no, I do think that if these are superconductors, which, as I said, now I'm inclined to believe they are not qualitatively different from the cuprates in the following sense. What I think is essential in the cuprates is that you have an insulator in the parent state, and then when you change one element by another one, you are doping holes into the copper oxygen planes in that case. And in this case, you're replacing, you also have oxygen, you have copper, you have lead, and you're replacing lead, which could be like a 4 plus ion, by copper, which is 2 plus, and that would also dope holes. And when you don't have copper, it's an insulator. And when you do the replacement, it does these things which suggest superconductivity. So I do think it's entirely possible that it's kind of the same physics that's going on in the cuprates.
Wow. Okay, I think I might have gotten this to work on the animation. Do you guys see this animation, Ina, on the screen?
I don't,
Okay,
but maybe the
maybe
audience does.
maybe it's not working. And maybe that's just because it's not sharing. Oh no, it's showing up on screen. Okay, cool. So on screen, I'm illustrating. This is a Richard B. Heel friend on Santa Barbara. He's got his own YouTube channel where he's showing, the kind of sine qua non of a superconductor, which is its resistance dropping versus temperature. And it starts off, and there's a phenomenon where it drops below what's called a critical temperature, which is not a delta function or a step function. There's linear resistance as you cool it down, then dropping to zero resistance when it's in the superconducting state over some small range in temperature. Jorge, when we talked last time, you had me convinced about Diaz's superconductor that that it was I don't want to say kind of fraudulent or misrepresented, but the fact was that that the magnetic susceptibility was really, that was the hallmark. And I want you to talk about that. But before you do, I want Ina just to clarify, could this just be very, very small resistance and just not possible to measure the difference even in a 4-wire measurement? Can you nerd out a little bit for my brilliant audience? Could this not just be very low resistance? I mean, is it truly convincing that it's zero resistance?
So let me clarify what I said a little bit. So uh, um, these papers are intriguing, but they're sometimes they have issues with the y-axis.
Aha.
So the
Let me try to bring up
resistivity.
the paper. I'm going to try to bring up the paper too, Ina. Is there a figure that I should look at? Figure 5 or something?
Yeah, figure 5.
Okay. Okay, so yeah, go on. I'll try to get this up.
Okay. I'm looking at it myself, and I probably won't be able to see your screen. But in any case, the y-axis of resistivity is 10 to the minus 2 ohm centimeters. So typically, for metals, we measure resistivity in micro ohm centimeters. So this scale is about 4 orders of magnitude larger than we would customarily do. So in the so-called normal state, I guess above 100 Celsius, this resistance is gigantic. It's orders of magnitude larger than kind of a a limit that is typically seen in a lot of metals. I mean, not in all materials, but that is a very large normal state resistance. And then if you go to where the resistance kind of plateaus, they drew a red guide to the eye. And if you trace that to the right-hand y-axis, you can see that it is not quite at zero. It's like a little bit above that zero line, and it's also drawn a little bit optimistically through the lowest temperature data. So
I see. Okay. So, yeah, I think I have the wrong paper. The one I'm looking at is this, is called, what is it called here? It's first room temperature, ambient pressure, superconductor by Lee, Kim, and Kwan.
No,
Is that
that's the other one. It's the other one.
Yeah, the one with the more authors. The
okay?
superconductor, what's its name, showing levitation at room temperature and atmospheric pressure and mechanism.
Okay, so I'll try to get that up. But Jorge, talk about the magnetization and that phenomena. We'll get into the Meisner effect in a minute, but what about
Yeah.
the magnetization
Yeah.
and why couldn't it be a diamagnet? I mean, Ina pointed out, like most of us are diamagnetic, right?
Yeah, let me just add to the resistance comments of Ina. I mean, it is true that it doesn't show zero resistance and it looks very weird. And I totally agree. When I first saw that graph, I wasn't convinced at all. But as I say, sometimes samples are inhomogeneous, and it can be that if there is not a continuous path, it won't go to zero resistance, even though there are superconducting. Now, going to susceptibility, you asked me about the Ranga-Diaz situation. And there it was a combination of things that made me believe that that wasn't real. And so the story there, as I told you last time, is I asked for the underlying raw data because there had been some subtraction of two different measurements made. And so the authors kind of didn't want to share the raw data. And that was a big red flag. And so when they finally shared the raw data, it was clear that the data had been manipulated and fabricated. But from the graphs themselves, you couldn't say for a fact this is not superconductivity or this is superconductivity. So, you look at the whole picture. But the point is, superconductivity is a very unique phenomenon. Okay, either it's there or it's not. It's macroscopic quantum physics at work. Okay, so there's no such thing as very small resistance. Okay, if it's a superconductor, it's a superconductor, and the resistance, if you have a homogeneous or sufficiently connected sample, is exactly zero. And you put in a supercurrent, and it will be there next year when you come back. So it's a qualitatively different state of matter. Okay, so as I say, when you look at the totality of evidence so far, it's conflicting, but if there is something like the levitation that I think is very hard to explain, and I do not think that normal diamagnetism, it's true, a lot of things are diamagnetic, but not with the necessary strength to explain, particularly the first video that only showed partial levitation. It looks like a quite thick sample that with normal diamagnetism of lead or graphite even, you wouldn't get.
You could obtain it, right? I see.
I have to leave now, Brian. So
What's that?
I will have to go now.
Oh, okay. Well, Jorge, thank you very much. It's wonderful to get your impression of this. I really appreciate your time, and hopefully we can do another interview with Lena together in person with you. That'd be great. Thanks, Jorge.
Thank you.
Bye.
Good to hear you again, Jorge.
Hi. Okay, so Ina, it's the two of us now. Let me just get his off of there, removed from the switcher. There we go. Okay, so I got the paper up and I was looking at the red line that you were talking about. One of the things that's always interesting to me is when somebody comes up with some, novel claim, which is of course wonderful, but then they come up with an explanation, for an alternative effect. In other words, they solve a problem, or they point out a problem in the existing model or paradigm, then they reinvent it or come up with a new invention. I'm thinking about people in cosmology that say want to reject the Big Bang or confirm some other model of theirs, and they come up with a new model. We just had a live stream with Alison Kirkpatrick of University of Kansas, about this very issue, where a scientist in Canada claims that the Webb telescope results are not consistent with the age of the universe. In fact, he comes up with the universe that's 26 billion years old, twice as big. And that's always kind of interesting. Not only point out a problem in an existing theory, but come up with a new theory. What do you make of this? That the theoretical results are, I heard, and I tweeted to you, for confirmation because you're my thread girl. Now there's too many thread boys out there, so that there's a thread girl now. Everyone should follow Ina Vishik on Twitter and elsewhere. I tweeted, what is this really confirming? I mean, it's a theoretical simulation. But I should say, again, reminding the viewers, you are not convinced. Jorge is convinced. It's actually the opposite of what I expected. So you're not convinced this is superconducting, and that's wonderful to hear the strong opinions. But tell me, what would convince you? What would you like to see besides raw data and a huge sample? And I'll sell you this one if you let me, babysit your kids or something. I don't know. Tell me, or you babysit my kids. How about that? So tell me, what would convince you, or what would make this more plausible? Is it the simulations? Was that adding to believability?
So there's, I guess, believability or verification. It's not a singular thing. It is a process, and the process will continue. I think beyond the current hype cycle. I want to see replication, and it should be noted that replication will take time. And if it's not replicatable, that'll take time. Like if your students do something for a week, I don't think you'll allow them to claim success or failure, as I will not either. So
Right.
it'll take time, even though in the paper they lay out the synthesis procedure. But from anecdote, when you follow the procedure in a different lab in a different location, oftentimes you need to make modifications. This happens all the time when people move to another university in another climate, another humidity. Believe it or not, even though the synthesis procedure might be rigorous, it does need to be kind of modified in a new environment sometimes. Yeah,
Mhm.
so I'm just waiting for replication, for I guess more different types of measurements, maybe. So I am, like I said, cautiously curious that something interesting might be going on. And in particular, one of the ways that this material sort of quacks like a duck is that its diamagnetic response, how it magnetizes opposite to the applied field, it does have some dependence on if it's cooled in a magnetic field versus not cooled in a magnetic field. So I'd be curious to see other types of measurements in a magnetic field, like even the crystal structure or something like
Mhm.
that.
And talk about the simulation that I kind of asked you about the other day on Twitter, at least.
Mhm.
They claim at LBNL using superconductor to obtain confirmation of superconducting pathways when you replace atomic substitution. What goes into such simulations? Although you're not a simulator, perhaps yourself, you must be familiar with the both outcomes and also the potential systematic effects of such simulations. So, what did you make of those simulations, and how should a layperson like me in this field apprise themselves of what to believe based on those simulations?
Yeah, so I guess I'm, like you said, I'm not an expert in these either. You should ask Sinead Griffin to be a guest. But what I will say is that these sorts of calculations are pretty standard. And let me just back up and say what was posted. So the calculation was not directly something to do with, is this material superconducting? How does it superconduct? Why does it superconduct? What was calculated was something called the electronic band structure, which it tells you how electrons move around in a material in the normal state when it's not superconducting. So to there's sort of these are pretty standard calculations. However, there are in this system, I believe, some approximations that need to be made, given the fact that you have some of the lead being replaced by copper. You have sort of a non-stoichiometric, as it's called, compound. So some approximations have to be made there. So the results of these electronic structure calculations was something that is currently a very hot topic in condensed matter physics. And what was reported was a flat band. So what that means in more common speak is that the electrons in this material, in the way that it was simulated, are predicted to move much slower than expected. So that means that the kinetic energy of electrons is small. And there's another energy scale associated with electrons in a material, and that is the fact that they're charged particles and they have Coulomb repulsion amongst themselves. So every electron repels every other electron. A lot of the time, amazingly, we can just ignore it because the kinetic energy is so large. But in this case, we cannot. So having a flat band does not tell you that you have a superconductor. Or that you necessarily have a propensity towards a superconductor. What it tells you, what we do know is in flat bands, you get a lot of interesting things kind of reliably happening. Sometimes you get superconductivity. Sometimes you get exotic type of magnetism. Sometimes you get the charges arranging themselves in weird ways. So it just is a fruitful platform for surprises in materials.
Okay, great. So we have a bunch more questions from the audience. What's the current status of replication, if you're aware of it more than I am, perhaps?
So there have been a number of papers posted on the archive, and maybe more as we're having this conversation. I don't want to comment too deeply because I haven't read them. But what I can say is that replication attempts are underway, and I can also say that you should not expect a definitive answer in such a short time period, because in experimental research, if you start doing something today that you haven't been doing for years prior, you're not going to probably reach the conclusion in 1 week.
All right. One of my listeners or viewers, T, is asking if it's not a superconductor, but instead has a tremendous, humongous diamagnetic constant, could that still have technological uses?
It could. So like for example, magnetic levitation, it relies on this effect. So potentially, just having a very good diamagnet could have uses.
Mm-hmm. And then we didn't get to really share your personal kind of thoughts about the technological implications or the, I don't know, cultural implications. This is like the discovery of the transistor. I mean, if it's true, let's just say it's true, which you're currently, and I think rightfully so, still skeptical, waiting for more replication data, evidence from accredited individuals, backing from laboratory, from theory backing, etc. But I should say sometimes that doesn't occur. I mean, Jorge has told me that he's not really that persuaded by BCS theory is the correct description and of adequately describing the Meisner effect, which I should show you on the screen because Richard Viheel put so much beautiful effort into it. I'll put that up in just a second. But anyway, talk to me about the technological implications and cultural, or how will it affect you? Admittedly, we're both nerds, but how would it affect the world potentially?
I guess, first of all, in bringing up Jorge's thoughts, you bring up an important point that we can have a superconductor without understanding why it becomes superconducting, without understanding the mechanism. And we can still, go through the process of engineering it, optimizing it to carry more current, optimizing it to be more phase pure, and so on and so forth. So a lot of progress can be made without understanding, as has been the case with the copper oxide high temperature superconductors, which at present day are the highest transition temperature at ambient pressure confirmed. But yeah, as far as technology, I think when you have a material that changes the world, no matter what its properties are that change the world, it's sometimes hard to predict the applications in such an early stage. So some of the things you described are some of the things that we know how to do with superconductors. We know how to transmit a large current with them. We know how to make a large electromagnet with them. But as an example of what I'm saying, let's go back 100 years to the low temperature superconductors that were discovered. And then 50 years or 40 years later, they were understood. There was a theory that many people accept about why they become superconducting. And then another 40 years later, in the 90s, people had the idea, hey, we can use these for quantum computing. And that is a new application that kind of took off, I guess, 90 years after the initial discovery of the superconductor. So I think the real applications, maybe we can't even envision them. The ones that we can envision them, maybe it will not be so cost effective.
Right. So I have a couple more questions from the audience in the last 10 minutes or so. Just a reminder, subscribe to the channel, leave a like if you want to see more episodes like this with friends of mine like Ina, Jorge, and other cosmologists. We're going to have a deep dive with my former professor at Brown University, Robert Brandenburger, who's presenting a new description of the early universe called string gas cosmology, which does away with inflation using string theory. And we went into a very, very deep dive on perturbation theory and all sorts of cosmological fun facts. I have an interview with Richard Ellis, who wrote a book over here about galaxies in the cosmos from an observer perspective. And we have interviews with Dave Farina, aka Professor Dave, and also upcoming ones with GadSad and other luminaries. So it's quite an exciting summer for the Into the Impossible podcast, especially joined at short notice by my friend and inspiration, Ina Vishik, professor at UC Davis. And so, I want to show the magnetic levitating effect, which also goes by the Meisner effect. Is this just like a parlor trick? Is this something that, you really think about on a daily basis? Is like, oh, if it had zero resistance and it was, had this first order phase or whatever, second order phase transition, whatever it has, I won't believe it until I actually see that it has the Meisner effect. Is this just a parlor trick, or is this something that we should all demand of all of our superconductors?
Are you talking about seeing a video?
Yeah, well, yeah. I mean, or just whatever. Does that have to be? Can you imagine a superconductor that's real, legitimate, etc., that doesn't exhibit the Meisner effect, or is this a requirement of a superconductor?
So I guess there's obscure cases where you don't get Meissner effect, like a so-called type 3 superconductor, but generally you get Meissner effect. It's one of the defining features of a superconductor. As far as like seeing it, like in pictures or videos, that's cute. But I guess what researchers really care about is a quantity called magnetic susceptibility. So it basically, you have a specimen, you apply a magnetic field, a known magnetic field, and you measure how much that material gets magnetized. And then you divide the two, and it gives you the susceptibility, which, as the name implies, tells you how susceptible is the material to getting magnetized by an applied field. So in a superconductor, what the signature is you have a negative susceptibility. So you apply a magnetic field, it gets magnetized opposite. And the size of this effect tends to be much larger than in ordinary diamagnets like us, like hydrogen, beryllium. There's a lot of the periodic table is diamagnetic. It's very common. But how superconductors differ is that it tends to be larger, and also there tends to be some so it tends to be larger in a superconductor. And one defining attribute of a superconductor that differs, for example, from a perfect conductor is, so if you have a perfect conductor, which doesn't exist in real life, but a hypothetical object, and it is in a magnetic field, and the flux lines penetrate your perfect conductor, you cool it down, the flux lines will stay. So it will not do, a perfect conductor doesn't care if when you cool it in a magnetic field. A superconductor,
Mhm.
if you cool it in a magnetic field, this is called field cooling. At the critical temperature Tc, when it becomes a superconductor, it will expel some or all of that magnetic field. So you'll get an onset of that right at Tc. And people that are experts in interpreting these kinds of measurements can look at sort of the difference in susceptibility between when you cool in magnetic field and you cool in zero magnetic field, and make statements about, how superconducting is this, what's the shielding fraction, all the stuff that is not my precise expertise.
I see. Okay, great. So now I'm going to show. So I've been showing the just the magnetic field expulsion, courtesy of Rich Behal's wonderful animations, and you're going to be seeing more of those. We have a video that I made about the LIGO implementation as a dark matter detector. So we're throwing everything together: aliens, superconductors, and dark matter detection. So now I'm going to show his video that he made of a. So this one, it shows a normal. It shows a superconductor suspended in a magnetic field by a wire, and then in a gravitational field. And for a normal metal, that metal does not expel the field, so it goes straight through it. And then I showed when the superconductivity is manifest as the temperature drops on the right below the critical temperature Tc, that the flux lines get expelled. Now I'm going to cut the supporting wire, and we're going to show the behavior when you have a normal metal, or the superconductors in its normal state. Then it's going to be levitated by magnetic field, and then we're going to turn it off by taking it above its critical temperature. So you'll be able to see this when you watch the replay and so forth. But here we go on the Meisner Effect Part 2, and this is called falling magnetic field. Okay, so now it's a superconductor. The temperature is going up. It goes above its critical temperature, normal behavior sets in, and the block of normal material then drops down and falls down. And we've seen there were several pictures and videos of this, and even a little speck of it from a apparently replicated sample, which was kind of cool to see as well. Okay, so there's there's a couple more questions in the last few minutes that Ina is gracing us with her presence, and that one comes from Amdred Lambda. Cool last name. Hopefully I'm not butchering your first name. And that is, why does superconducting energy charge associated with magnetic permeability in superconductive materials? I guess maybe why is the magnetic properties of an electrical zero resistance electrical conductor, why is that so relevant? Why do people care about that, Ina?
Why do they care about the expulsion of magnetic field?
Well, yeah, why are the magnetic properties relevant for, don't you only care about, the fact that it has zero resistance? That's going to lead to all the breakthroughs, right? The levitating trains, sure, that's cool. But the zero resistance, defeating global warming, everything, is that not going to come from its electrical lack of resistance?
As you know, there's a core topic in physics called electricity and magnetism. So the two phenomena do tend to go hand in hand.
That's right.
I will say, in the context of superconductivity research, when you have a new proposed superconductor, there's bad reasons something might have zero resistance. Maybe your wire shorted, as has probably happened in some reports. But when you have the onset of another effect at the same temperature, that kind of gives more credibility to the result, especially if that other effect is a signature of the phenomenon. So generally, in this field of research in condensed matter physics, we like to see lots of things happening to really make us more sure that we're seeing something real. And in a superconducting transition, a lot of things happen, and there's an opportunity for many different experiments to lend credibility.
Okay, someone named Temp, which is appropriate, I guess, says, hey, why are you both completely deflecting to mention the 2 replication successes from 2 Chinese universities in China rushing to take credit for South Korea's discovery? Well, as you know, I love to wade into culture wars, and so no, we're not deflecting it. We're not paid by China or anything like that. Temp, I don't. I didn't see your question, but anything to comment on the replication? I mean, you did mention it already. I don't think there's much to add, right, Ina?
Yeah, I'm not talking about it because I haven't read it, and this is just because things are coming in so fast. So yes, replication attempts are good, and we'll see how it plays out in the coming months.
Okay, my friend Ernesto is asking, are there implications for telescopes? So we use superconductors all the time for our bolometers that we use for the CMB, cosmic microwave background detection, but they're quite sensitive as they are. Getting to another type of superconductor would be interesting, but not perhaps as interesting as some of the other technologies like microwave kinetic inductance detectors, etc. Let's see what else we have here. Any other questions? So let's see, capability doubles. So levitation seems to be on everybody's mind, especially with regard to UFO disclosure and stuff. I've got a lot of interesting characters that do like this. And actually, I'm on an email thread with Brian Josephson and many other UFO aficionados. And I did just do an interview with Ryan Graves recently that you can find on my channel, one of the F-18 pilots who claims to have witness data to some events off the coast of the eastern United States. Anyway, any thoughts about advanced technology, maybe not of this Earth? Ina, could we say anything about that in the remaining minutes? That this could be the next great leap for humanity on our voyage to become interplanetary.
So no, but I guess you do have a colleague that potentially saw signatures of maybe minute superconductivity in extraterrestrial rocks. So it's that's the connection I have.
All right. So there's just a lot of really fun questions about the future and warp drives and can we use the flux tubes to take us back and teleport us back in time. I'm going to take the opportunity in the last 2 minutes that we have together to thank you so much, Ina, and refer people to follow Ina on Twitter at Ina Vishik, and I'll put a link to that in the show notes. I'll put your website in there as well. But Ina, as you know, as a longtime listener, I always like to ask deep existential questions. And I want to ask you 2, one of which is inspired by Arthur C. Clarke. I guess they're both inspired by Arthur C. Clarke. I'm honored to be the associate director of the Arthur C. Clarke Center for Human Imagination at UC San Diego. And the first one would be the quote that we open all of our podcasts with, which is in Arthur's voice, where he says, any sufficiently advanced technology is indistinguishable from magic. And I don't know, have you seen the movie 2001: A Space Odyssey?
No.
Okay, yeah, you're too young. But anyway, it's a famous, iconic movie. But one of the parts starts out. Did you see the Barbie movie?
No.
You didn't see the Barbie movie? Come on, don't tell me you saw Oppenheimer. Please don't tell me.
I'm at home watching Netflix with the littles.
Well, when you come visit me, we'll all go out. We'll take our girls out to see Barbie and Oppenheimer. I saw Oppenheimer. I didn't see Barbie. But Barbie apparently opens up with a scene that is evocative of 2001: A Space Odyssey, where these monkeys or primates are hitting this tablet with a bone. They don't really know what it is, and then they flip the bone, goes up in the air, and the girls in Barbie are hitting Barbie dolls and so forth, as I understand it. I'm going to be doing a video of the physics of Barbie soon. Stay tuned. No, I'm not going to do that. But the scene really comes from 2001: A Space Odyssey, where they find this monolith, and the monolith, we don't know what it is. Is it a time capsule? Is it a sentinel? Is it a watcher, a lurker? What is it? But I want to ask you in this way, what piece of technology to you is most or least distinguishable from magic? What is the most impressive technology as an experimental physicist that you've ever encountered? Maybe not in your own work. What's the most impressive thing that human beings have ever done?
Wow. That I have to admit, I haven't really thought of that. Um, I mean, it's hard to answer because technology is just everywhere, and um, I mean, I would say that our computers, our silicon-based electronics. It's strange for me to say this because it's sort of related to my field very closely,
No,
and
that's
I
totally fine.
know how all the components work, but the fact that you have so many transistors in such a small area and so many steps in the fabrication process, and then it's subjected to all kinds of environments, as you have it in your pocket and drive it around in a hot car and whatnot, take it through an x-ray machine at the airport, whatever, and it still works. So that is really remarkable when you think of it, and the capabilities sort of continue to increase. We have not hit the end of Moore's law yet, and I think this really illustrates just how central and almost magical material science and material physics is in our everyday world. And I'm really happy that with LK99, people are sort of appreciating one corner of this field.
Yeah, absolutely. Yeah, to find people debating on Twitter, is it type 2? Is it type 1? And it's pretty thrilling when the alternative is debating some indictment of a former president or something like that. Okay, last question. As you know, we have a lot of very brilliant technical minded guests and also audience members. Many of them are men, although not all. There's a good number that are female, and I'm proud that not only have I had on some of the greatest luminaries, but also people that are relatively lesser known, both male and female, of all different creeds and races and colors. But I want to ask you, in the form of the inspiration of the title of this podcast, which comes from Arthur C. Clarke's another saying of his, which is, the only way to determine the limits of the possible is to go beyond them into the impossible. That's where I got the name of the podcast. I want to ask you, in the form of advice to your younger self, you can include your experiences as a woman in a male-dominated field or not. It's up to you. But I want to give yourself advice. You have 30 seconds to talk to your 22-year-old self up at Stanford, graduate student or what have you. I want to ask you to kind of let me know, what would you tell that person to give them the courage to do as you've done, to go into the impossible?
Okay, so many young people, I was as well, are sometimes too courageous in in a sense. Like they can be reckless sometimes. So I'm not sure if courage is the limiting factor. But I guess the advice I would give to my younger self is to work harder. So in those early days when you don't have other responsibilities, that's really the time to set the foundation for your future career. And also, do not throw away your old problem sets and exams.
They may come in handy when you have to make your own problem sets and exams as a professor. Well,
Yeah.
Professor Ina Vishik, distinguished colleague of mine at the University of California System, the greatest university on the face of the earth. Can't wait till we can get our families together and hang out. It's been too long. And I wish you all the best. Thank you for taking our listeners on this deep dive into the physics behind the headlines and helping to explain and break down where we go from here. And I just want to wish you a great rest of your summer. And like I said, got to take the kids to see the physics of Barbenheimer.
Absolutely. Thanks for having me. And thank you for having the courage to delve into this thing that I know is far outside your everyday interests.
It is. Thank you, Ina. It's been great. So thanks, everybody. I hope you enjoyed this episode, deep dive into physics. No, we don't only talk about aliens on this podcast. Though, as you guys are noting, there are many different possibilities that technology could be advanced substantially if we were to somehow make contact in the future. But I will continue to discuss the breaking news in science. There are claims of so-called dark stars being observed by my friend Katie Fries at the University of Texas at Austin. And she's been a guest on the podcast before. And she and her team claim that they might have detected what are known as dark stars, which may provide new glimpses into dark matter. I'm going to try to get her back on the podcast. I'm going to take a couple days off, enjoy the summer now that it's finally gotten clear here in San Diego, and spend some time with the family. I urge you all to do that as well. And there's going to be huge breaking news on this podcast, at least with upcoming appearances by yours truly on some really foundational podcast shows. I've already sort of started to leak out some of that information. If you're on my Magic Monday mailing list, because any sufficiently advanced technology is indistinguishable from magic, I have a mailing list where I share the latest and greatest in technology and science and things I'm doing. And for those of you with an EDU email address, you're automatically guaranteed to win a meteorite. Maybe not this size. This is the one that I tricked Ina so cruelly into thinking was a sample of LK99. I wonder if that's more expensive than what I pay for these meteorites. But anyway, if you go to briankeating.com/list, you'll win, get a chance to win one of the next 100 meteorites that I do send out. But if you go to .edu, or if you go to briankeating.com/edu, meaning that you have an EDU address, either you're a professor, student, postdoc, what have you, go to this link right here, you'll win a meteorite for sure. Because my mission is to kind of gather and synthesize a cohort of all of you, the greatest minds on the earth, and kind of help guide you through the process of either high schoolers going into college students becoming better at their research and scholastic endeavors, and then graduate students, postdocs, faculty, etc. Because I think the future, of our humanity depends on this. And I think it's great for people like Musk and others to say, oh, we have to become interplanetary, but we have a lot of issues we can solve here on Earth, but only if we have a really astute, educated, erudite listening audience and educated populace. So I'm trying to connect 1 million minds in my multiverse of minds. And part of the way I do that is communicate through my mailing list, briankeating.com. So please do go to that, and we'll keep in touch. And stay tuned for, as I said, some huge appearances on at least 2 or 3 of the biggest podcast venues out there in the world, besides this one, where the brightest minds in the universe gather. So I hope you like it. Hope you'll share it. The channel's really grown a lot. Started the year with about 79,000 subscribers on YouTube, and we've almost doubled that. And hopefully we'll double more and exponentially and increase until the whole planet is a member of this magical multiverse that I am blessed to be partnering with you on. So enjoy the day. Send me suggestions. Follow on Twitter and Instagram, Dr. Brian Keating, YouTube, Dr. Brian Keating, and send me some suggestions for people. We had a deep dive into the claim of this very aged, hoary old universe, 26 billion year old universe. I did hear from the author, Professor Gupta at Ottawa, and he agreed with a lot of the things we presented, and we might have him on. So let me know. What do you want me to investigate? These news items, we can do a weekly news update. We can do more deep dives, more solo episodes. Check out my physics of Oppenheimer video, which has received is coming up on a great many views. So I'm pretty proud of that video, and then hopefully you'll enjoy and share the podcast with your friends and family that are interested in science and doing deep dives. I never dumb things down. I never ever want to be accused of doing that. So we have these great animations. Thank you, Richard Beheel from Santa Barbara. These were such a treat to have these. Let me know if you like these animations. If you want to see more, we're going to have a video about the physics behind LIGO, which is a gravitational wave observatory. But Richard has been working on some magical animations of how it can be used as a dark matter detector, combining some of the greatest unknown mysteries in all of science. So for now, your fearful host, Dr. Brian Keating, from the University of California, San Diego, and the Arthur C. Clarke Center for Human Imagination. Thanking you for spending so much of your time with me and imploring you to stay tuned and hit that notification bell, because you're not going to miss some of the upcoming podcasts, interviews, deep dives, and some appearances by yours truly on other people's podcasts. Signing off, Brian Keating.